Okay, this is the answer to a request we had for a little review of the exponent laws and the corresponding log laws. And so let's start there. Um, for any exponent law, and the exponent laws seem to go pretty well for people. The Unit 5 test, we had very good results. People seem to understand these exponent laws pretty well. Very little in the way of difficulties there. Great scores. Um, but somehow the connection oftentimes is lost to the log laws, and a little review is probably necessary. So, for any exponent law, there's a corresponding log law. And by that I mean if you have two numbers with the same base multiplied, right, then you add the exponents. So as a concrete example, obviously if we have x squared times x to the third, that's going to be x to the fifth, right? Because x squared means you're multiplying two x's, and x to the third means you're multiplying three x's. And so in totality, what? You're multiplying five x's. So that's what's going on there. Well, for that exponent law, there's a corresponding log law, namely that the log of a product is the sum of the logs. So when you multiply two numbers with the same base, you add the exponents. And you can see that same thing happening here. When you're looking at log laws, all you're looking at is the exponent part. Think of it that way and see if that doesn't form the connection you need here. Now, similarly, when you look at the quotient rule, right? Quotient rule for log laws says the log of a quotient is the difference of the logs. Well, why is that? Where's that come from? Well, it comes from our exponent laws, and when you divide two expressions that have the same base. And of course, what do you do when you divide two expressions that have the same base? Well, you subtract those exponents. And again, if we just make up a trivial example here, we have x to the sixth, say, divided by x squared. Well, this x to the sixth is a shorthand notation for six x's being multiplied together, and then that's being divided by two x's multiplied together. Now, since multiplication and division are inverse operations, that results in x to the fourth. And so really all you do is you subtract the exponents, you get your answer. Now with that in mind, what about x to the fifth, say, as a concrete example, divided by x to the fifth? Well, first of all, anytime you divide a quantity by itself, you get 1. One little caveat, yes, one little caveat there. X cannot be 0 because you can't divide by 0, right? Now, in terms of our exponent laws, we know that when we divide, we subtract the two exponents. So in this concrete example, we have 5 minus 5. Well, that corresponds to x to the 0 power. Now, by transitivity, what do we know? We know that x to the 0 power is 1, provided x does not equal 0, because you can see in here if you allowed x to be 0, then you'd be allowing a division by 0, and we don't want to do that. All right. So that's where that log law is coming from. Now, if you look at the power to a power rule on the exponent side of the ledger, right here, x to the a raised to the b, that means b, x to the a's multiplied together. Well, you're going to multiply those exponents, right? So x to the a to the b power is x to the ab. And that's where this log law right here is coming from. All right. The log, you can think of the log as an exponent. As a general overarching idea, if you think log is exponent, that can oftentimes ground you and keep you where you want your head to be on these things. So right here, this log a, think of it as an exponent, and it's being raised to a power. Well, what do we do when we raise a power to a power? We multiply the powers. The a gets multiplied times the b. And so we have log a times the b. So that's where that's coming from. Now, on the exponent side of the ledger, of course, we know anything to the first power is that anything. And so on the log side of the ledger, we know that the log base n of n is 1, right? In other words, log base 10 of 10 is 1. Because where does that come from? Well, this idea right here. Log is exponent. Log is as in equals, right? Is as in equals. A log is an exponent. So that 1, that's an exponent. And it's an exponent of some base. And the base is right here. The base is the 10. So 10 to the first power equals what? Well, of course, 10 to the first power equals 10. Okay? Now, just to continue with that concept a little bit, because this is where people kind of tend to lose it. You want to look at a number, say, like this log base 3 of 8. And you want to look at that, and in your mind's eye, you should know that's a little bit less than 2. It's a little bit smaller than 2, so I put 2 a little minus sign up there, right? Indicating it's 1 decimal something, and a little bit less than 2. Now, how do I know that? Well, if I go to my exponents, I know that 3 to the first power is, of course, 3. And I know that 3 to the second power is 9. Well, this says to me, this log base 3 of 8 is saying to me 3 to what power is 8? Well, again, I know that 3 to the second is 9. So this number that this thing represents has to be a little bit smaller than 2. All right. So if you keep in mind when you read these log things, the little number subscripted here, that's your base. And that base is being raised to this power. All right. So log is an exponent. And the result is this number here. Right. Then it will get to be as easy as, when you look at square root of 50, right? Square root of 50. Yeah, okay, that's about 7, right? And nobody has any, it's a little bit, touch bigger than 7, right? It's around 7, and you know it just by looking at it. With time and with practice, you will get to that point with logarithms where you'll look at a logarithmic number and know the relative size of it. All right, that's just sort of bringing your numeracy up. All right. Now, in terms of now using these things, right, to solve equations, let's for a minute suppose that you've got 4 to the x minus 1 power equals 8. Okay? So there's what? An exponential. That's an exponential equation, right? Meaning the variable right there, the variable is an exponent. Okay? So one technique to solve exponential equations, one way we do that is something called the common base technique. All right? Which just means you get the two base numbers, which are 4 and 8. You get the two base numbers to be the same thing. Now, you have to think, and again, it sort of comes down to numeracy. Are 4 and 8 exponentially connected? And they are. 4 can be written as 2 squared, and then that's being raised to the x minus 1 power. And 8 is 2 to the third power. All right? And of course, you see that because you know your powers of 2, your powers of 3, your powers of 5. You want to have those things available in a working knowledge. Now, right here on the left, we're raising a power to a power. So we're going to use this third exponent law right here. X to the a to the b power is x to the ab. And when I do that, I want to be careful. I've got to distribute that 2. So it's going to be 2x minus 2. Make sure you understand what happened here on the left. And on the right, I'm just going to leave it as 2 to the third. And now the idea is you've got the same base number, right? The expressions as wholes are equal. Those are the same thing. They got an equal sign between them, right? So if the bases are the same and the expressions in totality are the same, then it must be that 2x minus 2 equals 3. And now you're in the land of elementary algebra. We use the additive inverse, and we get 2x equals 5, and we divide by 2, and we get x equals the 5 halves power. And of course, the 5 halves power means um, that our exponent is 5 halves minus 1, right? So if we take that back and look at that value, we've got 5 halves minus 1 is supposedly equal to 8, right? So 1 is 2 halves, right? So that's 4 to the 5 halves minus 2 halves is 3 halves. And what does this fractional exponent mean? Well, the top of that thing is the power, and the bottom is the root, right? So when you have a fractional exponent, in this case, I'm looking at the square root of 4, and then that result is being taken to the third power. Now, I could do the 4 to the third first and then do the square root if I wanted to. Typically, people do the root first because it makes the number smaller. All right. Now, the square root of 4, well known to be 2. And then we're going to cube that, right? And 2 cubed, of course, is 8. And on the right-hand side, we have an 8. So indeed, it checks. All right. So that's what's going on with those exponent equations and obtaining a common base. Now, there is another technique. You can use a logarithmic technique, and the logarithmic technique relies on you being able to work these log laws. So as an example, let me write an equation in here. Um, let's see, 3 to the x minus 1 equals, um, doesn't really matter, I'll say 15. Okay. Now again, have your numeracy kick in right here, right? Think about this. 3 to some power is 15. Well, you know 3 squared is 9, right? And 3 cube would be 27. So this x minus 1 right here has to be between 2 and 3. All right? So you want to develop that sense of the size your answer needs to be. All right? With practice, it's not too difficult. Now, 3, the base 3, and the base 15 are not exponentially connected. Yes, 15 is 5 times 3, but that's not an exponential connection. That's a multiplication connection. Okay? So I'm not going to be able to obtain a common base here. Instead, what I'm going to do is log both sides. Now, don't let the log syntax blow you away. We're just applying log techniques here. And we got log 3 to the x minus 1 power equals log 15. Now, on the left, you have a log law in place. You've got the log of a to the b power. This log law that we put this oval around earlier. That's what I'm seeing. And so it's based on this third exponent law, raising a power to a power, you multiply the powers. And so this x minus 1 right here, I'm going to bring that and multiply it times the log of 3. And over here, log 15. Now, normally, when you see a set of parentheses, you get highly trained in elementary algebra that this is something called the distributive property, and so you distribute the log 3, and you could do that. You could do that, okay? But instead, since I want to solve for x, I'm going to divide, because it's multiplication, I'm going to divide both sides by log 3, just like this. And of course that cancels over there just like it does under normal elementary algebra. And we've got x minus 1 equals log 15 divided by log 3. And then this 1 we'll bring to the other side. And of course use the property of the additive inverse. And so we got log 15 divided by log 3 plus 1. So in essence, how do you solve exponential equations, whether it's by common base method or by this logarithmic method that I've just demonstrated here? The answer is you don't. You instead turn them into multiplication problems and solve them using the normal elementary algebra principles um, and the inverse operations of division and subtraction, addition, that sort of thing. Okay. Now, the only other thing I'll mention, and we'll shut this down, is this expression right here, log 15 divided by log 3. All right. There is another way we can notate that. We could notate that as log base 3 of 15, and that's something from the high school realm called the change of base formula. Change of base formula. Now, that's sort of just an overview. There's a lot more you can talk about with regard to this topic, but hopefully this will get you through the unit 6 and you'll be comfortable with these logarithmic ideas. Um, Learn to read the log expressions, right? 3 to some power is 15. So, okay, that number is a little bit bigger than 2, right? Because I know that 3 squared, again, I know 3 squared is 9, and I know that 3 cubed is 27. So I'm looking at this and I'm thinking 3 to some power is 15. Well, that power is going to have to be a little bigger than 2. So see if this doesn't help you. And if you have more questions about logarithms or exponential equations or how to solve those sorts of things, let us know. Watch the Unit 6 pretest video, see if that helps. And if you do have more questions, don't hesitate to get back to us.